Hello, my name is Verena Schlott, and I'm going to present to you our paper W-ADE, Timing Performance Benchmarking in Web of Things for the ICWE2020 conference. First, I'm going to give you a quick overview of the state of the art of Web of Things. The Web of Things, also called the application layer of the Internet of Things, faces some severe problems as universal standards are missing. Therefore, vendors come up with their own implementations and protocols. And this leads to a fragmentation and interoperability issues, especially when multiple IoT devices need to be connected together into one mashup. It requires complex integration work, technical expertise, and time to create heterogeneous scenarios. The W3C Web of Things approach tries to cope with this fragmentation and the lack of interoperability across IoT platforms. The goal is to preserve and complement existing IoT standards and solutions. The core building block of this approach is the thing description. A thing description semantically describes a thing's metadata, interfaces, available protocols, and access links, indicating its functionality. Thing interactions are modeled as properties, actions, and events. Let's come to the problem that motivated our work. With the help of the thing description, the communication between IoT devices based on different protocols can be standardized. Beyond that, the thing description also allows to design mashups without having the actual devices at disposal. But to create reliable TD-based mashups, it is inevitable to have data on the timing performance of the included things. This is especially important if involved interactions trigger physical processes, as these can take a considerable amount of time. Timing performance information is also required when a mashup is very complex and thing interactions have dependencies on each other responses or when included things are not available, as then individual interaction types cannot be measured. At the moment, the TD does not provide such information. To obtain data on timing performance for each different protocol, a compatible service has to be started and timing performance has to be measured manually. There is no application capable of measuring timing performance, generating timing performance benchmarks, and at the same time supporting diverse IoT protocols. To sum this up, there are no timing performance benchmarks included in the thing description. Therefore, an unremovable uncertainty about timing performance exists upon deployment, and there is no available data on execution times, which would be needed to design optimal mashup scenarios. Further, there is no vocabulary which could describe timing performance in a TD. And these facts are embedded in a bigger problem, which is the lack of a testing and development environment for thing descriptions. The mentioned problems forms the research questions. How can the timing performance for things and mashup scenarios be guaranteed in a systematic way? To answer this question, we made three main contributions in our paper. First, we allow system designers to invoke single interactions of a thing independent from its protocol based only on its TD and retrieve the associated timing performance. Secondly, we introduce a technique to automatically produce static and dynamic timing performance benchmarks with estimations for worst, best, and average execution times, together with computed confidence interval limits. And our third contribution is the provision of a vocabulary set which is aligned with the thing description specification and can be used to annotate TDs with observed timing performance. This results in the following scientific relevance. We provide a timing performance benchmarking system for the Web of Things. With our technique, we make an optimization during design time possible. We provide the missing foundation block for improved development and testing of thing descriptions. And last, we propose a suited vocabulary set for timing performance benchmarks and a way to annotate existing TDs with it. Now, I'll introduce you to W-ADE, the system that builds the foundation of all our contributions. W-ADE, short for API Development Environment for Web of Things, is an application that takes thing description as inputs and is able to return them, annotated with timing performance information. Plugins can be easily integrated, and it can also be extended with diverse protocols, making it able to communicate with all IoT devices. W-ADE is able to parse TDs, generate input fields for interactions for the user, execute interactions, and display results, including the measured time. I show you how this works in a quick demo of W-ADE itself. This is W-ADE's user interface. By clicking this button, we can add a new thing description, and we can either paste our thing description here, load an example TD, or paste from a URI. The thing description is now loaded and parsed, generating these buttons. These are the properties, actions, and events which are inside the thing description. We can now select single interactions, add the possible input parameters, select them, and now invoke them. The results are presented here on the right side. Here, this is the selected interaction. This is the return, the time it took to get this return, the input size or output size if applicable. And here we have an event awaiting. However, the core feature of W-ADE is the generation of timing performance benchmarks and the annotation of existing thing description with this data. Our objective was to make timing performance benchmarking possible with any IoT thing on any system, in any network, and using any protocol. A problem is that users cannot necessarily access the thing's application for an analysis. Another difficulty is that information on the network environment might be missing or is not accessible either. And that information about the system cannot be guaranteed. Taking these objectives, as well as the constraints into account, we formulated our dynamic timing prediction as follows. Whereby T total of X is the time needed for transferring a message from a consumer to a thing to invoke an interaction X, whereby a consumer describes another device, a browser, or a web application that is able to understand thing descriptions and interact with things. T client of X describes the client-side process time. T transfer of X describes the time needed for sending and receiving a message over the network. And finally, T process stands for the process time of our target thing. This includes, for example, the physical interaction time. Although the influences of T client and T transfer cannot be isolated reliably, it is possible under certain circumstances to differentiate between action, hence time-consuming physical or virtual processes, and property execution times, and to retrieve the static timing of action interactions. With the fulfilled prerequisites that an IoT device offers a property and an action interaction, it solely sends responses after a physical or internal process is finished, and the application logic is comparable for all existing interactions. We can make the following assumptions about static timing prediction. Here, T static of X stands for the supposed static time of an action X. T total of X describes the dynamic time of the invoked action X, and T total of Y describes the dynamic time of an invoked property interaction Y. To provide meaningful timing performance benchmarks for thing interactions, our technique determines the estimated worst case, best case, and average execution time of all measurements. Since we cannot guarantee that things can be analyzed, they are treated as black box components and therefore estimated worst case and best case execution times are utilized. To offer reliable benchmarks, confidence intervals are used to propose a range of plausible values for the average execution times. This graphic visually explains our technique. By executing an interaction for several repetitions for a specific amount of time, while simultaneously measuring the elapsed time, we can combine measurements and generate these results. With the prior chosen confidence interval, the confidence interval of the average execution time can be computed. As certain factors, such as initial connection establishment, memory, caching, etc., can have a great impact on measurements, we detect outliers with the help of interquartile range. We allow measurements to be executed multiple times. We allow an optional delay before each measurement or before the start of the overall measurements. We remove the first measured values, and we segment results into realistic and possible, whereby possible results include all measurements and realistic results measurements where outliers have been removed. Further, to make use of these benchmarks, we developed a suited vocabulary set which describes the measured data and is aligned with the TD specification. With the help of this timing interaction vocabulary, a thing description can be annotated. I will now show you how this is implemented in W-ADE. Now let's see the performance implementation in W-ADE. We can now select the properties, same when we were in the editor. We can put the input parameters. Now here we can choose the type of measurement, either iteration or duration. By duration, we can enter the duration in milliseconds. When we select iteration, we can enter the number of iterations. We say 3. Now we can add a delay. It's optional. We can add a delay before each or delay before beginning, but we add no delay. Here's the delay in milliseconds. Now we can say how many times we want to measure with the settings, but we only say 1 time. Now we can choose the confidence interval. We choose 99.9%. The static timing is only available if we selected 1 property and 1 action interaction, but we selected 2 properties, so this is not available. Now we can start the measurements. The results are presented here on the right side. When we click, we can show all measurements. If we show result button, we have the realistic and possible measurements, and the first measurement, which is not included inside these. Now we have the worst case, best case, and average case, and average execution time, and all executions that were used for this computation. For realistic, there can be the only possibly outliers are removed. We have the confidence interval minimum, the confidence interval maximum, and for possible looks the same. We can also see the settings we did before. We can now either save this output as a JSON file, or we can annotate the existing TD we have in our editor and add this information to it. When we click this button, it is saved to our local system. To prove the correctness and validate the quality of our technique, we conducted 3 virtual experiments and 1 use case scenario with a physical IoT device. In the following, I'll describe 2 of them. The goal of this validity test was to validate W-ADE's time and performance measurement functionality. We wanted to show that processed results are consistent. To do so, we conducted a test with 1,000 property read requests and repeated this 10 times with a confidence interval of 99.9%. The results show that W-ADE's measured confidence intervals of the realistic average execution times, here depicted in blue, and of the possible average execution times, here depicted in orange, always lied within a 5% range around the average values. Moreover, average execution times always lied inside their own confidence interval and inside all other confidence intervals. This proves the validity of W-ADE. We also conducted 2 experiments to evaluate our static timing technique, and one was a use case with an actual IoT device. We wanted to demonstrate the practicability of static timing performance with a real thing. The utilized thing you can see in this picture was a pan tilt head module. It is a small robot arm that can pan and tilt. We invoked the action scan. The scan action makes the arm move from the outer left to the outer right for 100 times. And the property pan position, which reads the current pan position, also invoked 100 times. The chosen confidence interval was 99.9%, and we repeated this 10 times. The results show that we could measure a static timing, or we could get a static timing. And with this experiment, we showed that W-ADE enables users to get static timing performance of a physical interaction on an actual IoT device. The other experiments are described in detail in our paper, as well as the 2 I presented right now. But of course, we also found some limitations and issues that should be addressed in future work. While experimenting, we realized that the network environment, for example, due to delays, can have an influence on measurements. We also found that interactions can have a strong dependence towards other interactions. In future work, optional load tests, meaning the connection of multiple clients with the tested thing, should be integrated. And also the mentioned limitations need to be addressed. To finish my talk, I want to present you our conclusion and summarize this presentation. W-ADE facilitates the automated generation of reliable timing performance benchmarks while considering environmental influences. It enables the generation of static and dynamic timing performance benchmarks. Further, it is able to annotate TDs with this data. And optimization during design time is made possible. Additionally, W-ADE acts as testing and development environment for thing descriptions and as a platform for the W3C Web of Things ecosystem. You can see a short summary. For further details, explanations, and references, please read our paper, W-ADE Timing Performance Benchmarking Web of Things. Thank you very much.